Hello, calculus fans! We're going to talk about mixing problems now. So imagine we have a tank, usually a tank of water, and it's got a mixed solution of some substance, typically salt. But it doesn't have to be. We can dissolve anything we like, fluorine or bromine or something like that. Now we're going to have a solution pouring into the tank at a fixed rate, and we're going to pretend that the tank stays thoroughly mixed. So maybe you have some salt water coming in, and then we have a mixing mechanism that keeps the salt in the tank thoroughly mixed into the water. The mixture is also leaving the tank at a particular rate, and that rate could differ from the rate at which it's entering. Now let's let y of t denote the amount of the dissolved substance in the tank at time t. And then let y prime is the rate at which the substance is being added minus the rate at which it's being removed. Now we're going to be able to use this for a wide variety of physical phenomena. That is, salt dissolved in tanks, chemical reactions, maybe we want to clean pollutants from a water reservoir. We can also use this to model drugs in the bloodstream of a patient. All of these fit the model reasonably well. So let's do an example. A tank of water contains 10 kilograms of salt designed in 4,000 liters of water. Now a salt solution, and that's usually you call that brine, contains 0.1 kilograms of salt per liter. So there's a salty water comes into the tank, and that comes in at the rate of 50 liters per minute. And this solution is kept thoroughly mixed. So you got a mixing mechanism in the tank that just constantly churns the water in the tank and makes sure that the water that's in the tank is mixed up. We want the salt in the water to be mixed up. We don't want it high concentration in one part of the tank and low concentration somewhere else. Now the solution is going to be kept thoroughly mixed, and then it drains out from the tank at the same rate. And we want to know how much salt remains in the tank after 20 minutes. So at time equals 0, there's 10 kilograms of salt. How much will be in there at the end? So let's let y of t be the amount of salt in kilograms in the tank after t minutes. Now I want to make sure it's clear what y of t represents. If we boil off all the water, so we're just left with salt, the mass of that salt is what y of t is. So it doesn't have anything to do with the water, it has to do with how much salt is in the tank. We know that y of 0 is equal to 10 because that was our initial amount of salt that was dissolved in the water. We want to find y of 20 because we're asking what happens after 20 minutes. So what I'd like to do is create a differential equation that's satisfied by y of t. Now dy by dt is the rate of change of the amount of salt. And the way we can write this is to say that dy by dt is the rate in minus the rate out. So rate in is the rate at which the salt enters the tank, and rate out is the rate at which the salt leaves the tank. So let's figure out what rate in. It's 0.01 kilograms per liter. That's the concentration of the salt water coming in, and it's coming in at the rate of 50 liters per minute. So if we multiply those, so rate in is 0.01 kilograms per liter. That was the concentration of the brine coming in, and it's coming in at the rate of 50 liters per minute. We multiply those to get 0.5 kilograms per minute. Notice that the units cancel out. That's how we end up with kilograms per minute, which we should have known from the beginning that we were going to end up with kilograms per minute because we're measuring dy by dt. Y is measured in kilograms, t is measured in minutes. Now our tank always contains 4,000 liters because the flow rate in and the flow rate out is the same, so we're not gaining or losing any water. That means the concentration of the salt in the tank at time t is y of t over 4,000. Now the water flows out at the rate of 50 liters per minute, so our rate out is y of t over 4,000 kilograms per liter times 50 liters per minute. And that gives us y of t over 80 kilograms per minute. So the rate out also has to be measured in kilograms per minute. All right, so we can write down what our differential equation is now. dy by dt is 0.5 minus y of t over 80. We can rewrite this as 40 minus y of t over 80. And what we're going to do is separate variables. So we'll divide by 40 minus y, so we'll divide by this, and we'll multiply by dt. So we get dy over 40 minus y equals dt over 80. Usual game, we integrate both sides. And so on the left-hand side, we get negative log of the absolute value of 40 minus y, and on the right side, we get t over 80 plus c. Where's this minus sign come from? That's our chain rule factor. Now keep in mind that we said that y of 0 is equal to 20. So if we plug all that in, we get negative log 20 equals c. So that gives us a solution. Negative log of absolute value of 40 minus y is equal to t over 80 minus log 20. Now if we do a little algebra, we can get absolute value of 40 minus y is equal to 20e to the minus t over 80. Don't take my word for it. Work it out. Try to solve for this absolute value expression. Now getting rid of the absolute value is a little more difficult. Now y of t is continuous because it represents a physical quantity with no abrupt changes. Y of t measures the amount of salt in the tank. We're not dropping salt blocks into the tank to abruptly change the amount of salt. There's a continuous change by having the water flow in. Now y of 0 is equal to 20, and the right-hand side is never 0. That tells us that 40 minus y is always positive, which means we can drop the absolute value. So we can conclude that 40 minus y is equal to 20 e to the minus t over 80. And if we solve for y, we'll get 40 minus 20 e to the minus t over 80. So if we want to plug in t equals 20, no problem. Y of 20 is equal to 40 minus 20 e to the minus 20 over 80. And that's approximately 24.4 kilograms. So that's what we were trying to solve for. So the amount of salt in the tank is going up, and I think you can see that by the fact that the concentration that we started with is actually lower than the concentration of the water that's coming into the tank. Okay, that's all for now.